Is the recording?
Yeah, recording is in progress. Yeah.
Okay. So, greetings, everyone. It is my pleasure to welcome you all to this webinar organized by IEEE DEIS Young Professionals. And the webinar is titled Arc Flash Hazard and Electrical Safety. And our distinguished speaker for today's session is Wei-Jen Lee. And as the committee member of the DEIS YP, I have the honor to introduce myself as Sneha Hegde. Thank you for joining us. As a friendly reminder, we have a few housekeeping notes. We would like to inform you that this webinar is being recorded. Please be mindful that any questions formulated during this session will be included in the recording and will be accessible to the public. The slides and the video will be made available on the IEEE DIS websites and the YouTube accounts, and the link to the video will be provided within 48 hours. We kindly request you that you reserve your questions until the end of the presentation. And during the question and answer session, please unmute yourself in an orderly manner to ask your questions. Alternatively, you may also use the chat feature to post your questions, which we will address soon after the presentation. To ensure the quality of the call, we kindly request you that you mute your line during the presentation. If you encounter any technical issues, please use the chat box to request assistance. The speaker today, Professor Lee, has received BS and MS degrees from National Taiwan University in Taipei, Taiwan, and a PhD degree from the University of Texas, Arlington in 1978, 1980, and 1985, respectively, all in electrical engineering. In 1986, he joined the University of Texas at Arlington, where he is currently a professor of electrical engineering department and director of the Energy Systems Research Center. He has also been involved in the revision of several IEEE standards and development. He is the chair of IEEE TAB, Technical Activity Board Climate Change Program, co-chair of IEEE Sustainable Development Ad Hoc Committee, member of Ad Hoc Committee to coordinate IEEE response to climate change, member of IEEE TAB Hall of Honor, and the chair of IEEE Smart Grid Program. And he has also been involved in several research subjects such as utility deregulation, renewable energy, arc flash hazards, electrical safety, smart grids, and several other topics. He has also served as a primary investigator and co-primary investigator of over 100 funded research projects. He has published more than 210 journal papers, 310 conference proceedings. He has provided on-site training courses for power engineers in Panama, China, Taiwan, and many other countries. Professor Lee is a fellow of IEEE, member of National Academy of Inventors, and registered professional engineer in the state of Texas. We welcome you today to this webinar. Thank you so much for accepting to be a part of your webinar series. Without any further delay, the stage is yours.
Okay. Well, good day, everybody. And it is my pleasure to be here and to give the discussion on one of my research topics, which is also related to the IEEE standard development. And because this is a DIS, so that I have some other research which are not related. So I give the several topics for the committee to choose, and they choose this one here. So I would like to share that select the Windows screen here. Okay. So can everybody still see my screen?
Yes, we can see your screen. Thank you.
Okay. Yeah, the topic I would like to discuss with you today is arc flash hazard and the electrical safeties. And this is also directly related to the 2018 edition of the IEEE Standard 1584-2018, the guide for performing arc flash hazard calculations. And for this one here, yeah, as I have mentioned, these topics they are related to the dielectric air breakdown. Okay, so Well, we know that electricity. We basically we enjoy the electricity, and since the 1882 September 4th, 1882, that Thomas Edison started with his first commercial electrical utility service company in New York. And we also realized, soon after that, we also realized, in addition to the electrical shock, if there's not proper installed, electricity can also cause a fire. And so, yes, while we are enjoying the electricity, then that we also face some side effect or dangers of the electricity. And although the electrical incident, it has a relatively small percentage of all work-related incident, because we know that electrical can be dangerous. And however, they are disproportionately fatal. And in case of burn, they may result in an extended hospitalization and rehabilitations. So if you look at all from the OSHA record, the electrical related fatality is number 5 leading cause of the death in the workplace. So on this way here, that the different organization has to develop the standards to protect the safety of the workers. And the two famous one is the NFPA 70E, that's a National Fire Protection Association. The other one is IEEE 1584 that I would like to discuss with you today. So what the first one, let's talk about what is arc flush. And so in the electric arc, it's a basically considered as the electrical breakdown of the airs. And it can occur where there's a sufficient voltage in the electrical system and a path to ground or low voltage. And for this one here, it's basically normally we have when we design the electrical system, we have enough gap over there, so they don't happen that often. However, during the maintenance or in some operation, that in the substation, sometimes we call it a screwdriver alert. And the so-called screwdriver alert is the people when the worker working in the substation or work on the equipment, then he or she dropped the screwdriver accidentally and touched the too hot component, and then they create a short circuit. Once they create a short circuit, the energy will heat up the surrounding air and ionize the air. So even though the screwdriver may bounce away, however, since this is ionized air, then the arc or the current continue flow. And since it is not a zero impedance, so according to the I square R, it's going to generate the heat. And then since this happens so fast, so it becomes a burst. So sometimes we call in the arc flush term, sometimes call it arc burst. And so that is basically it's a sudden release and then cause the destruction of the equipment and cause fire or sometimes injury or even kill the worker and all the nearby peoples. So this is one of the example here, and it happened in South America in the substation, and you can download this video clip from YouTube. So you can see here as a worker, the incident that basically happened when the worker tried to rack in the circuit breaker, and because of the misalignment in the back panel, that caused a short circuit, and then all of a sudden that created the arc flush. So everything seems so normal, and then all of a sudden it just happened. So you can see here, okay, this is some picture I got it from the internet, and then that's the burning that basically, okay, well, can be the with the personal protective equipment, then basically that sometimes they punch through and then cause some injury of the workers. So when we design the protection, then normally you have to follow some standards, and this is the in the arc rush professional. Then we use the so-called Stoll curve. This is an Army doctor, Alice Stoll, and with her associate that they work together, and then in 1960s developed this standard. This one here, this is the one currently people are using, 1.2 calorie per centimeter square per second. So this is become a de facto number that when people try to design the protection. And we call this one is a Stoll curve. And even those at the different time frame, the human will be able to absorb a little bit more energy here. However, then in the industry, we use this number, 1.2 calorie per centimeter square per second here. And so all the design when we try to protect the people is try to put the personal protection equipment. So on that way, you will be able to reduce the heat touch to the human skin and limit it to the 1.2 calorie per centimeter square per second. And for this number, that according to the Alice, the Dr. Stoll, that this is has a 50% chance human will develop the second-degree burn on the human skin. And so this is the industry standard. It's basically what would be the PPE, what you have to wear on at the 4 calorie per centimeter square, 8, 25, and 40. And normally, if it is above the 40 calorie per centimeter square per second, we will recommend do not work the electrical system live. And so the reason why we want this kinds of protection, sometimes you will wonder why not just to put in the highest protection. And this is the different category you can see here. For this one, that the people can still move very freely, and it's very easy to work with. Once you wear on this one here, then become very cumbersome. And so in the environment, especially like in Texas, we have a very hot summer. Then if you wear this kinds of protection, then probably you can only wear about 10 minutes, and then you have to take it off and take a break. And also, if you're wearing this kinds of the protection gear, then it becomes very cumbersome, and sometimes they create a chance for accident. So too much protection is not necessarily good things in the personal protection equipment arena. So there's a long history. People try to understand what is the arc rush, and even at that time we know it caused hazard. However, it was difficult to quantify it. So in the first publication from the IEEE is in the 1584, 2002. And at that time, okay, basically because we have a limited understanding on the system, so they only proposed the two configuration. We call this one. This is an electro, and this is a vertical electro. Then they are in the enclosure. So this is the measurement equipment over there. They try to measure the heat flux. And this is basically follow the ASTM 1959 and try to mimic the human skin, the heat absorption or heat exposure. Okay, so you can look at the ASTM 1959 for the design spec on this one here. And this is in the open air situation. Again, this is the calorimeter you have over there, and you can see at the center, it's a copper disc. And for the copper disc, it's the 4 centimeter in diameter, 1.6 millimeter in thickness. So total weight is 18 grams. And so on this one here, you measure the temperature rise and you convert it into the calorie per centimeter square per second. So after the 1584 2002 publication, and then people realized, okay, several areas of dark flash phenomena and the very range of the model need further research and the test validation. And also, after the publication, people think, okay, 2 configurations are not enough. So some possible configuration should be also be considered. And then also in the 2002 model, you basically, people also point out in some configurations, the arc current is higher than the body fault current, which is physically it's not possible because during the arc, then you insert a resistor into the loop. So theoretically, you should receive a lower current. But in the model calculation, the formula they provided, and that give a contrary result. And then also, because of the model development procedure over there, then they use the 1000 volt as a breaking point. So at the 1000 minus and 1000 plus, they have a discontinuity point. However, at that time, we did not have other standard to reference. So people kind of accept the fact and use it widely among industry. So in 2004, basically right after the publication of 2002, then IEEE and NFPA get together, form a task group, a steering committee, and then they try to do a further validation on the arc flash and ready for the next revision, which is published in the 2018. So we try to look at it, this one here, basically the arc flash. When you talk about arc flash, very important one is looking for the plasma trajectory. And so on this way here, this is one of the vertical open air, which is one of the configuration in the 2002, 1584 2002. And you can see here, when you have a vertical configuration, the trajectory of the plasma is going downward. And this one here, at this position here, we mimic the location of the worker. So on this configuration, you will see that the lower part of the body will be basically, okay, exposed under the plasma. Then the other one is the horizontal one. And the horizontal one was not discussed in the 2002 standard. However, this one created the most serious injury on the arc flash event, because when you look at this one here, the plasma, the people, when you look at it, okay, this is the worker standard here, and you can see that the plasma basically moved toward, directed to the people, and then if you pay a little more attention here, that actually they push. The pressure has pushed this one, the center part tilted a little bit. Okay, so in addition to the thermal, and actually the pressure of the plasma, also basically the flow is also a concern. Especially sometimes they will knock people out of the ladder. And then this is the one that the configure similar to the 2002 model. However, the electrode were extended to the bottom of the enclosure. And you can see here, this is the 4 kV system and 63 kA short circuit, both arcing fault. And you can see, okay, the plume come out. And if you pay attention here, along the wall, you're going to see a dot. Okay, so that is the melted copper, basically shoot about 30 feet away. And so even this one here, it seems a long time, but this is the high-speed video. So the actual whole event is about 100 milliseconds. So on this one, in 2008, I was invited to serve as a project manager for the next revision of the development. And we would like to do basically because the the situation is quite dynamic. So it's very difficult to use a mathematical model. Even we also try to use a mathematical model to understand the physics of the plasma and the physics of backflash. However, a lot of development is based on the experiment. And the difference between the 2002 model and the 2018 is on the 2002 model, they are based on about 300 tests. In the 2018 model, we have run more than 2,000 tests, and among them, about 1,800 tests were used for the model development. And also in the 2018 revision, we have a 5 configuration. So let's move to the standard by cell. Okay, and this guide is provide a model and an analytical process to enable calculation of the predicted thermal incident energy and the arc flash boundary. The reason why we call it the arc flash boundary, if you visit the plant, and then normally basically you are the visitor. Sometimes they ask you to wear eyeglasses or ear plug and hard hat. So this is the basic protection. However, it doesn't protect the arc flash, so they will ask you to stay on basically on the floor. Sometimes they draw a line or have a different color coded, and they ask you to stay behind certain distance, and we call that one is arc flash boundary. In other words, that basically if you stay behind that line, then the possible to receive the thermal energy will be less than 1.2 calorie per centimeter squared. And for this standard, we basically developed the model that fit into the 208 to 15 kV. So we didn't go beyond. And for the below the 208 volt, that's possible. The possibility to have a sustainable arc will be less. Okay. So this one is designed for the qualified person to use it. And of course, if you look at the 2002 model, it's rather simple. You are inside a box or outside a box. And for the 2018 model, it's a little bit complicated, and that requires some physics background. Okay, and so on this one here, we don't, for the assumption is basically we are looking for a 3-phase fault. We don't consider a single phase or a DC current, even though that we are doing some additional work on try to work on the single phase and the DC system. However, we don't have enough information to publish or develop the model yet. And we don't use this one because when you consider the PPE, they have other considerations. So this is just one of the parameters. It doesn't cover all the required information for the PPE selection. And one very important aspect is, okay, where to stop. And basically, so in the 2002 model, they tell the people or the practitioner that it's less than 240 volt, and if the transformer is less than 125 kVA, then there's a less possibility to have a sustainable arc. But during the experiment, then I found that that even with that level, you may still have a sustainable arc. So that I run the test with the UL underwriter representative. So in the 70E, that they changed the model, they changed the description, and then referred it back to the 1584. So in the new revision of the 1584, then we put in the statement saying, okay, sustainable arcs are possible, but less likely in 3-phase system operating at the 240 nominal or less, with an available short circuit current less than 2000 amps. And when you look at this one here, 240 volt nominal, and in the power system, normally we consider plus minus 50%, 5%. So it's basically, when we run the testing, it's 252 volt. Okay, so this is the range that you look at it. Okay, so we basically divide into 2 parts, is 208 to 600 and 600 to 15 kV. and they have a different, because of the configuration and because of the voltage, then the sustainable arc will be different, so that you're going to have a different gap over there, and the frequency is the 50 and the 60 hertz. We consider this 3-phase. Okay, and for the enclosure dimension, we work up to, actually it's a 50-inch, and so when you try to perform the arc flash analysis, then of course the first one, you have to understand the configuration and obtain the parameters. So the first part, if you look at this one here, the equation over there, the first one you have to look at it, what is your short circuit current? Because on the short circuit current, we consider the impedance, shows the fault impedance is equal to 0. So from the calculation point of view, because R equal to 0, so you are not going to create any heat. And then based on the short circuit current, based on your configuration, then you try to estimate what is the arcing current. And from the arcing current, you go back to look at the relay curve or your fuse burning curve. Then you try to estimate your arc duration. Okay, so this is the basically determine how long the arc will last. And then also you try to determine the working distance, because we always tell people time and distance are your best friend in the arc flash scenario. So if you are further away, then that you basically, even there's an arc flash, then it will not get hurt. And also, if you can reduce the duration, then that will basically reduce the energy release. And so with that, all the information, you try to estimate the instant energy, and you try to calculate the protection boundary. So yes, this one here, that actually create a lot of discussion, okay, what configuration to choose. And so we went back to the very simple, the fundamental physics side, and we call it basically right-hand rule, or that basically you consider this is your flux, this is your current, and this is your force direction here. This is the current flow into here, and basically create a flux. And then this is the arcing current at here, that represent I at here, and this one B, this is the B side, and so that basically give you the estimation or prediction of the trajectory, plasma trajectory. And with the plasma trajectory, then you try, when you determine the configuration, then that the trajectory will become a major factor for you to determine that what configuration you should use in your estimation. So for example, on this one here, even a simple same equivalent here, if the arc flash happened at here, then we consider, because the trajectory, according to the trajectory, it will move down. The plasma will move down. We consider this is the VCB or VOA situation. You can see here, okay, the plasma basically come down. And then, however, if you look at this one here, if the happen here, for example, if this is the happen at here, okay, people try to use the improper multimeter, try to plug in here, and then create a flash. So on this way here, that become a horizontal one. Then you can see here, okay. So the same equipment at the different, if it happened at different location, they are going, you have to use a different configuration. And here you can see that it's basically the evidence that the black mark here the created by the horizontal blast, and here is created by the vertical blast. So on this way here, then how to apply the model, and of course you can reference the 1584.1, that basically on the application side, and the .2 will be on the data collection, and .2 is under development, so it will be published in the near future. So for this one here, if I have a one-line diagram, this is the one-line diagram of the system, then you have to collect all the information. So you say, okay, well, if I have a arc flash happen at here, then what will be the different scenario? If it happen it's on the 480 volt, then this is the second scenario. So on this way here, then you try to look at it, because in the system configuration, when you try to ask for the information from the utility, they will give you a range of the impedance, or give you a range of the short circuit current here, or we call it the driving point impedance. Then you try to calculate if something happened here, it's a short circuit happened here, what would be your maximum short circuit current? What would be your minimum short circuit current? And similarly, at this point, what is your maximum short circuit current? And what is your minimum short circuit current? And for this one here, then in the previous one, we consider this is the SCB configuration. The other one is the VCBB configuration. This is the first thing that you have to decide. And then, so on the calculation side, because the arcing current vary during the event, so you try to look at the average arcing current and your minimum arcing current. Okay, sometimes we call it the low bound arcing current. So on each case, you are going to have a full configuration. To basically, you have to analyze four possible scenario. One is the maximum current, and then calculate average arcing current, calculate the minimum arcing current on this one here, and you calculate the average arcing current and minimum arcing current. So for each point, then you are going to have a full studies. And lower current doesn't mean lower incident energy, because the lower current means that you're going to have a longer arc duration, because the relay operation and or the fuse blowing, it depends on the current goes through the device. So when you have a low current, then that the fault will last longer before they are clear. So even they have a from the unit time point of view, they produce less instant energy. However, for the overall event, they can be the worst. Okay, so on this way here, that just repeat the model here and repeat the parameter here. You have a 13.8 kV system, and what is your gap? The gap is you consider, okay, the distance between the electrode here, and what is the working distance that basically people from the arc point and to the chest of the worker, and then all the enclosure size. Then, so this is the summary of the calculation, because we did not have enough time to run through all the detailed calculation. I just give you the result. Okay, so this is the maximum current. And this, I just give you the two scenario here. This is the lower current, lower bound. This is the highest current, the average arcing current, and you can see arc duration according to the fuse curve. That is about the same time, because they are in the same grade. And then they basically push into that we call it's a current limiting the arena, and then the correction factor here, a current correction factor, and then the size correction factor. Then basically try to look at this is the basically, because we are doing the low bound, so the average is the considered unity. So the low bound, you reduce it, and then the instant energy on this one here, the maximum current produce higher energy. Higher instant energy on this one is 8.99 calorie per centimeter square, and this one is the 7.27. So this is the protection boundary. It's about 3 meters away. This is 2.7 meters. So from the calculation, you know the maximum bulk current with the average arcing current solution yield the highest instant energy. And this is the calculator. Okay, so for the calculator on this one here, this is the one that we have developed, and you can download this calculator Excel file from the IEEE data port. Okay, so on this way here, that is basically that since this is a relatively simple calculation over there, so we did not look at the fuse curve. This is the user input information. So for example, on this one here, the configuration, It's one is the VCP, vertical electrode, inside the box, and the VCPP number 2 is the vertical electrode with the barrier inside the box and with the barrier, and this one is the horizontal. This is the open air, vertical, open air, horizontal. So you enter the number here that indicate the configuration. And then you enter the open circuit voltage. So what is the voltage on the system? In this case, it's 13.8 kV. And what is your baudiful current based on the short circuit current calculation? You enter the number here. It's as I have shown you, the previous one is 18.241, and the gap is 6 inch. And since the IEEE is going to the metric system, so we basically converted from the imperial unit to the metric system. And the working distance, it's a 914, so that is basically it's a 24 inch. And because normally you consider it's an 18 inch or 24 inch, because this is arm length. We consider it's arm length. And then arc duration here, this is basically based on the fuse curve or relay curve. And this is the configuration. Okay, what is the size of the enclosure? And this is the estimation result. So blue field is the user input area, and the yellow field is the calculation result. And so to accommodate the need for the current limiting fuse, we also create this one here. And because for the current limiting fuse, once you are in the current limiting sector, then the let-through current will be much less than the arcing current. So we create this field for the user input, and on that one, they can have a good estimation on the instant energy. So yeah, you are more than welcome to download this one here. Since if you are IEEE member, you will be able to access this information free of charge. And there are four download over there. One is the disclaimer, description, and the second one is the user menu, and the third one is the average current. Okay, and then the fourth one is the low bound current. If you look at the extension of the file name, okay, one is the millimeter, okay, when we developed it, and then this one here with the capital M over there is a modified. We call it a modified. It's a low bound arcing current. And a similar situation for the 480 volt calculation here, and this one here is a VCPP vertical cube and with the barrier. And again, we have a two maximum short circuit current and the minimum short circuit current, and the different configuration over there. So when you do the calculation, and then for the minimum short circuit current with the low bound, yes, it's on the 17 kA, and the maximum current is the 20 kA. So behind on this one here, we follow a fuse curve. So operation time, you can see here at this current, they operate at about 70 milliseconds. And however, at the low current, the fuse operated at 240 milliseconds. And with all the same information, you can see here on this case, it has a 2.5 carat per centimeter square. The protection boundary is less than 1 meter away. And for this one here, that basically the arcing current, okay, the instant energy is about 7 carats per centimeter square, even with the lower current. And the protection boundary is about 1.6 meter away. So you can see here when you look at the problem, that the low current doesn't mean a lower instant energy. You also have to consider the operation time of the relay or circuit breakers. And this is also the calculation result, and the result basically match the calculation that here. I'm just using one example here, and this is the second one, 6.95. You can see here, and this is basically the copy the result from match the result from the calculator here. And yeah, in the arc flash has a point of view that this one here, all the measurement we have done, it's more like an average. And so this is the closed loop. This is the basically measurement point, and this is copper disc. However, you can see on the insulation side, sometimes you're going to have a metal droplet over there. So yeah, that is the basically, okay, that part we could not measure. And that also, this kinds of phenomena will also create the damage. And it also considered is a hazard. Okay, so this one here, this is one of the major equipment I have used, the ND filter. And you can see here, this is about 10 feet away. And you can see a metal drop, the copper droplet on top of the lens. And of course, it's basically damaged the lens. And imagine if you don't wear a safety glass and this incident happened and that metal droplet basically drop into the human's eye, then it's going to cause us a permanent damage. So we always tell people you only have one pair, no spare. So when you get this environment, make sure you have a proper protection. And with that concludes my presentation. And if you have any question, you can, this is my QR code. You can scan it, and then my information is over there. So yeah, if you have any question, I'll be more than happy to answer.
Thank you so much. First, I wanted to express my gratitude to our speaker, Wei-Jen, for delivering such an informative presentation and for sharing your valuable insights on this topic. So now let's move on to the Q&A session. So we have few questions in the chat box. The first one is by Dodi Ismoyo. That arc explosion will only happen after the worker rack in the circuit breaker into the electrical panel and press the connect switch on button, or it can also happen.
No, it happened because the back panel is still alive. So you don't switch. You basically, before you have the chance to switch, then it happened.
So the second part of the question is, or it can also happen after the worker rack in the circuit breaker only without pressing the switch on connect button.
Yeah, that's correct.
Yeah. And I hope it has answered your question. And we have the second question from the calming. In what condition will the arc condition larger than the bolted short circuit current?
Well, this is the basically that people that's the reason why that we perform additional testing, because in the model development, because for the model development you base on your variable test point to run through the curve fitting and develop the formula. So in the 2002 model, people criticize that in some situation, in some configuration you input, your arcing current is higher than your bolted for current. As I have mentioned, this is from the physics point of view, this is not true. And so on this one here, that is you have to look at it and on the model development side. And that is the reason why we have a 2018, that the revision over there. And of course, in the field testing, that in my opinion, especially on high voltage, it is possible. Okay, it's because it really depends. And for example, I have run the test in a very cold weather. So if you run a test on a very cold weather over there, then especially when you basically set up the equipment, normally we call it a short circuit test in the afternoon. And then the next morning, you come into the lab, you start your arc flash testing. Then at that time, the temperature is dropping, so the resistor is also dropping. Then basically that short circuit current can be higher than the one that you have run the test or you try to calibrate the previous state. So that at high voltage, the short circuit current and the the arcing current are quite close. So sometimes that creates some difficulty in the model development. So in this revision, the 2018 revision, we took that part into consideration and did some correction over there. So it did not happen that in the 2018 formula that the arcing current is always smaller than the short circuit current.
We have the third question from MS Roy. How to consider for more than 15 kilovolt with lower fault, for example, up to 31.5 kiloampere? Why high kilovolt was not considered? Is it due to the fact that we cannot correlate the experiments for higher kilovolts? Are you planning anything for higher kilovolts beyond 15 kilovolt?
Yeah, that is a very good question. And because this standard was sponsored by the Industrial Application Society. And most of the industry facility, they are using a 13.8 kV. So at the time when they submit a PAR, for the standard development, we call it a project authorization request. And they state that their high voltage is 15 kV. And of course, it's possible to extend it. And of course, that you have to also look at if we try to extend the model, that require additional testing, and it is possible. So in the discussion, actually, I also expressed my idea because according to the IEEE standard, their share life is 10 years. So every 10 years, you have to do some revision or you have to do reballoting. And this will be a good point or a good area for us to expand for the next revision. Yeah, I know people are working on 35 kV, and there's a lot of discussion that try to extend the model to the 35 kV.
We have another question again from the same attendee. Is this arc flash happen when the arc suppression medium is missing or leaking out from the switchgear, for example, SF6 chamber?
It can happen this way. Yes, I have seen the incident actually happen last year in a utility company when they basically extract SF6 out of the circuit breaker, and then the worker forget. They try to energize it and then cause the arcing over there, and basically cause a big power interruption. Yes, this is the basic. But in that kind of incident, normally it's not going to. It's basically less likely to hurt people. And for the arc flash on this one here, as I have mentioned, this is from the Industrial Application Society. And we have, okay, in the industry, we have a so-called arc resistance enclosure. So basically, you try to confine the arc flash when it happened inside the enclosure. However, the study, when we try to perform this kind of analysis, is you are doing the maintenance. If you are doing the maintenance, you open the door. So your arc resistant feature is basically disappear. So you are directly exposed to the trajectory if the arc flash happen. And of course, when I have mentioned, normally when we design it, we have basically based on the BIL, the basic impulse level, to design the gap between the conductors. And this happen is sometimes people are working on the equipment and they drop the tool and then create a short circuit. Once they create a short circuit, they ionize the air, and then the arc continues to evolve until the circuit breaker open.
We have another question from one of our attendees, Sarah. Would it be possible to send the link of the calculator that you had just shown during the presentation?
Yes, I'll send a link to you. Yes.
Maybe you can just post it in the chat so that everyone can have access
Yeah.
to the.
Okay. I'll post in the. Let me that. Okay. So I will post it in the. Let me see the chat here. Okay. So this is the link.
Yes. We have another question from Mayur Gupta. What is the arc current factor?
What do you mean current? Okay, the factor over there, as I have mentioned, we have a two calculation. One calculate the average arcing current, and then we take the two standard deviation out on the lower part. So once you calculate the average, because the arcing current change during the incident. So the first calculation, first round of the calculation, we calculate the average arcing current. And after that, we take the two standard deviation. We consider it's a 95% confidence interval. And then that mark as a low bound current. And that is the factor that we put it in. And then in the industry, they basically use that one to estimate what will be the operation time of your fuse or relay.
Maybe we can just take one last question because we still have a lot of questions in the chat. How effective are arc flash protected switchgear? One of the switchgear I know has pressure monitoring switch, which operates at pressure less than 10 millibar. What is your view if we need arc flash PPE while dealing with such switchgears?
Well, when you try to look at this one here, you try to look at whether if anything happened or an accident happened, will that impact the worker or the worker will be exposed in that environment. Okay, so that is also the reason why when I developed the calculator over there, and then you can see the proximal trajectory is very important. If you confine everything inside, then you are safe because it doesn't the worker doesn't expose to the danger or to the hazard.
Tariq, please go ahead if you have a question.
Hi, Professor Lee. Thank you very much for your talk. Actually, I work in dielectric materials, but now I'm working on a flame retardancy of dielectric materials.
Okay.
And the thermal conductivity enhancement as well. So I'm doing the cone calorimeter on dielectric material to check the flame retardancy of that. But in terms of arc flash and this one, if I want to test that electrical insulating material, so what standard I have to use that? Because for the flame retardancy, I'm simply using cone calorimeter. But when it comes to the arc flash, here is a more electrical perspectives, because in cone calorimeter, we don't consider electrical perspectives, right? So
Yeah, this
what do you?
one here, normally even this is an electrical one, we pretty much consider the thermal side, how much energy that is going to generate, okay? Because we call that basically when you look at the arc, then we have a so-called arc column. A column has a resistor over there. When the current flow through the arc column, it's going to generate the heat. So even within 100 millisecond, so depends on the voltage, depends on the current. Then in some case, we can generate about that close to 1 million joules.
Okay.
Okay. So this is the more on the, this part is more considered the thermal. We don't consider the dielectric because the in the situation on the arc flash is more like air breakdown.
Oh.
Okay, and of course, some people also study on this one here in the electrical field that when you have a different elevation, the breakdown voltage will be lower. Okay, so that is the basically, this is also the that is more on the equipment design. That what kinds of gap that you have, that is basically follow the, when you design the gap, or the, we consider so-called the BIL, the basic impulse level, that follow the IEEE C37.
And why are you using that unit for arc energy intensity measurement? Is a Kelvin per centimeter square? Because in cone calorimeter, usually the heat flux is measured in a watt per meter square, a kilowatt per centimeter
But
square.
you consider time.
Okay.
So that become an energy.
Oh, okay.
Because when you reach to the human skin, is the energy, accumulated energy, that affect that the basically cause the degree, the burn injury. So we basically consider the time, consider the power, and then you aggregate it, become an energy, how much energy attached or the human skin is exposed.
Okay. Yeah, thank you very much, Professor Lee.
You're welcome.
I thank you so much for answering so many questions. And I think with this, we'll conclude our webinar. I would like to thank Wei-Jen for his time and for sharing your knowledge today. And I would also like to thank our attendees for their contribution and questions. So we have in the coming month our speaker Jinliang He, who's going to give a webinar on polypropylene-based cable insulation materials on July 11th. So we will be releasing the registration link soon. Stay tuned for the forthcoming webinars. Thank you and see you soon. Thank you, everyone.
All right. Well, thank you for the opportunity to discuss with you. And then if you have a question, yeah, please reach out to me.
Yes. Thank you.
You're welcome.
Thank you, everyone.